Jai Hind everyone, welcome back, and today we are going to learn about next topic, and that is quantum mechanics. So in quantum mechanics, I'll give you an introduction of this, and in quantum mechanics, first topic we will taking is a black body radiation, which is very important, black body radiation. So what is black body radiation? As you can see, solid when heated emit radiation varying over a wide range of wavelengths. For example, when we heat solid, color changes will continue to change with a further increase in temperature. That means if you heat one solid, then it will change its color, and that color will change because of the temperature. So this change in color happens from a lower frequency region to a high frequency region as temperature increases. So when you increase the temperature from little to higher, then that particular solid will radiate some heat with different frequency, and that is from lower frequency region to a high frequency region. For example, in many cases it changes from red to blue. An ideal body which can emit and absorb radiation of all frequency is called black body. So this is very important. An ideal body which can emit or absorb all frequencies is called a black body. A black body is an object that absorbs 100% of the radiation incident on. That means anything which can absorb everything but do not radiate anything is called a black body. So the first question which arises in our mind, whether an ideal black body exists or no, and that the answer is no. Because if you heat any object very high temperature, at very high temperature, then it will somehow radiate some type of radiation from it. So ideally we don't have any very good black body, but we can create one. So therefore it reflects no radiation and appears perfectly black. It is also a perfect emitter of radiation. At a particular temperature, the black body would emit the maximum amount of energy possible for that temperature, and the radiation emitted by such body is called black body radiation. So you can see a black body spectrum over here. A graph was obtained between energy density and wavelength at different temperature as shown. So one experiment has been done, and some bodies get heated, and what type of parameters they got. So this is my wavelength and this is my energy density, and you can see over here, you can see particularly over here that they all have same wavelength over here, and while they increase their temperature, if we increase the temperature at 3500, it start emitting black. On 4000 it start blue or violet, you can say. On 4500 it start emitting the dark blue, and green on 5000, and red on 5500K. So if you see that at some particular point or some particular wavelength they are not emitting anything, but after that their peak got different, and because of their different peak they will get a different color. And if you see here also, after the 1500 their value becomes almost equal to here also. But what you observe when you heat something, when you heat a body very high, then all the peaks get shifted towards a lower frequency. This is a low frequency and this is a high frequency. So ideal case has to be a bell shape. An ideal case should be a bell shape. It means half you can see over here and half you can see over here. But is it the case in black body radiation? The answer is no, and you will see that when they all got heated, all the system gets shifted towards the lower frequency. So we will take one by one. The experiment results are: the emission from black body at any temperature consists radiation of all wavelengths. All wavelengths, you are getting all the wavelengths. Second, at a given temperature, the energy is not uniformly distributed. As temperature of black body increases, the intensity of radiation for each wavelength increases. So you can see they are not equally distributed. As I said, explained, it has to be a bell-shaped curve for everything. What is has to be? It has to be like this. It has to be like this for one, this for second, this for third, this for fourth, and so on, if they are equally distributed. But this is not a case over here. Okay. So the second point, at a given temperature, the energy is not uniformly distributed. I have explained it. And as the temperature of black body increases, the intensity of radiation for each wavelength also increases. The amount of radiant energy emitted is small at very short and very long wave. See over here, I explained it, this part and this part. So at very low and at very high frequency, nothing has emitted, but in between their value is varied. So this is my third point. And the wavelength corresponding to a maximum energy represented by the peak of the curve shift towards a shorter wavelength. I explained it that the peak of all the wavelength gets shifted towards the lower frequency part. Wavelength part, sorry. Curve shift towards a shorter wavelength as temperature increases. That means there is an inverse relation between temperature and a wavelength. So we can say from here, and this is a very important law which is called Wien's law, Wien's displacement law, which says that lambda mt, that means lambda m, maximum value of lambda into T is a constant. And it says my lambda and temperature are inversely proportional to each other. So this shows as temperature increases, the black body emits a radiation of shorter wavelength. So that's why I am saying that lambda T is equal to constant will explain that my lambda is inversely proportional to a temperature. That means they have an inverse relation. If temperature increases, wavelength decreases, and vice versa. Okay. So now the second term which comes in the mind is called Stephen's law. So what is Stephen's law? When a black body is heated, it emits a radiation of all possible wavelengths. We understand that from the previous discussion. The scientist Stephen gave a law for energy distribution among the different wavelengths, and Stephen's law gave a total energy rated by a black body, and this is according to that point. So what he says? He says my all energy, previously what we learned, lambda T is equal to a constant. Is a constant. Okay. And Stephen says my energy distribution depends upon temperature, and that temperature is not direct, but it is the direct proportional of fourth power of the time. So he never says that E is proportional to T. No, he says my energy is proportional to T, but with the condition that it must have a degree of 4. That much high temperature has to be there to get some energy from out of it. So we say E is proportional to T to the power 4, and if we replace this proportional sign, then we can write equal to sigma T to the power 4. So this is my Stephen's law. where the constant of proportionality sigma is called Stephen-Boltzmann constant and has a value equal to sigma 5.6704 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. This is very important point. This is very important while we are doing some MCQs or we are doing some numerical value. So Stephen deduced from their previous knowledge that energy can be generated if you give a temperature, very high temperature, sorry, if you give very high temperature. Okay. Again, the Wien's displacement law, I told you before also. So what he investigated? He says Wien investigated the energy distribution over different wavelengths, and this law determines at what wavelength the intensity of radiation emitted from a black body reaches its maximum point. So after this point, the intensity decreases. So what he said? He said, we can see from here, and he said when lower part and higher wavelength, we are not getting anything. This is seen here and here also. And in between, if we increase the temperature, my energy got increased. We got some peak. But what else? When we further increase the temperature, they are rolling back. This is the maximum value. So you can see from here also that this is my maximum value. When we are increasing the temperature to 550, I got maximum value at this point, and when I further increase the temperature, it's rolling down. It's rolling down. In every case you can see. In 5000, it is increasing, and when you increase it a little bit, then its value got decreases. And this is what observed by the Wien. So what he said? He investigated that the energy distribution over a different wavelength, and this law determined at what temperature, what wavelength the intensity of radiation emitted from a black body reaches its maximum point. After this point, please mark this, after this point the intensity decreases as temperature increases, as I explained you earlier. So if you increase temperature after some threshold value, then you will not get energy, but your value will get decreased over there. After this point, the intensity decreases and temperature increases, and this creates a characteristic shape for that body radiation curve, which shows that a maximum energy point shift towards a shorter wavelength. I explained you this thing little while. So he says that lambda mt is not a constant, but he gave a value of that constant, and he said that my lambda m, the maximum value of lambda into time, is equal to b, and that b is some constant. And what is that? Where lambda m is the wavelength corresponding to maximum energy emission from a black body at absolute temperature T, and b is called Wien's displacement constant, and he gave that value as 0.00029 meter per time. So this is law of radiation formula. So here we are getting Wien's, that one is a displacement law and this is a radiation law. So Wien showed that the amount of radiation E lambda d lambda emitted by a unit area of black body per second at a temperature of T Kelvin in wavelength range between lambda and lambda plus d lambda. Here lambda plus d lambda means when we increase the value from that threshold value to some little more. So we can say lambda plus d lambda is given by the formula. E lambda d lambda is equal to A lambda by 5 F lambda T d lambda. And here this is very important. You have to learn this. this is some one formula, and it says that A by lambda to the power 5 function of lambda t d lambda. So the important part is this, and that is the equation we are getting is in the form of lambda and t in terms of wavelength and time in Kelvin. So we can say if I'll say A is equal to y, okay, y is equal to A sin lambda plus E lambda dt, this type of thing. So this is something which we can say a function of time, function of these two. So we will get a function of this. Okay. So where A is a constant and function lambda t is a function of product of lambda and t, and this is a Wien's formula, and therefore he also proved that maximum energy emitted by a black body is proportional to the fifth part of its absolute temperature. Hence he said that energy emitted at particular lambda is proportional to t to the power 5. So in Stefan's law, he says E is proportional to t to the power 4, and he says that my E lambda at particular wavelength, my maximum value can be emitted or generated or observed at t to the power 5. So we can take this down, and E lambda max is E upon t to the power is nothing but a constant, and this approaches a data at a shorter wavelength, but it deviates at longer. So some laws deviates at higher frequency wavelength and some at low. So this approaches data at shorter, but it deviates at longer wavelength. That means his formula, this particular formula, holds good for the shorter wavelength, but did not justify its value at longer wavelength. So again we have one more, what is Rayleigh's, and again some other person came and he also gave his deductions on these, and he said low Rayleigh used to classical theories of electromagnetism and thermodynamics to show that black body spectral energy distribution is given by. So we have to learn that. We need not to go very deep into it in engineering, but we must learn that. So E lambda is equal to 8 pi kt upon lambda to the power 4, and where k is a Boltzmann constant. 8 is a constant, pi is a constant, k is a constant, t and lambda is a constant. So it approaches the data at longer wavelength, but it deviates at shorter wavelength. So again, in the previous one, it holds good for the shorter wavelength, but not for the longer wavelength. But here it is going for the longer wavelength, but not for the shorter wavelength. Now we'll get a very important quantum theory of radiation and Planck's constant or Planck's law. So we'll take this and then we'll move to some other point. In 1900, Planck developed a theory of black body radiation that leads to an equation of energy density of the radiation. This equation is in complete agreement with the experimental observation, and he assumed that the atom of the wall of a black body behave as oscillators, and each has characteristic equation of oscillation. So we have learned this. So what he said? He said that energy of an oscillator can only have certain discrete value, and that is E is equal to NH nu. So he said En is equal to NH nu, where H is a Planck's constant, mu is a frequency, and why we are using it. See, for E1 that is H mu, for E2 this is twice H nu, 3 H nu, 4 H nu, and so on. Okay, so where n is a positive integer called the quantum number, and mu is a frequency of oscillator, and h is the Planck's constant. And this says that the energy is quantized. Energy is quantized, and each discrete energy value corresponding to different quantum state. How we can understand it? We can say that each energy level, if we say E1, I am giving just example, this is not actual one, but this way we can use it. Okay. The oscillator emit or absorb energy only in the form of packets of energy and not continuously. That means it is getting all the value in digit form, not continuously. In discrete form it is getting, and he says in the form of packets of energy and not continuously. And when making a transition from one quantum state to another, the entire different energy difference between the initial and final state in the transition emitted and absorbed as a quantum. And we know this. As I explained you, delta E is equal to delta n h nu and E2 minus E1. When we are moving from one energy level, this is my E1, this is my E2, and if I want to jump from here to here, to what, there must be a change in value of energy E2 minus E1, and that is equal to N2 minus N1 h nu. And why? If they have the same value, then nothing will happen. It has to be at lower energy level, and it has to be at higher energy level. And then if there is a difference, there is a need of getting some energy, then only something can go from E2 to E1, otherwise it will not. So we'll read this. This is very important, and wave particle duality. As we have learned that light can work as a ray and a wave, here also we have something which is a wave particle duality. So a particle means an object with a definite position in space which can't be simultaneously occupied by another particle and specified by their properties such as mass, momentum, kinetic energy and velocity. What he says? He says a particle, if something is said to be particle, then it must have a mass, it must have a momentum, it must have a energy, it must have a velocity. Otherwise, it will not be considered as a particle. On the other hand, if something is said to be wave, then it must have a frequency, it should have a energy, and it should have a momentum. So two or more waves can coexist in same region or superimpose to form a resultant wave, and the particle and wave properties of radiation can never be observed simultaneously. So sometimes it can behave as a particle, and sometimes it will behave as a wave with their properties of mass, momentum, kinetic energy, velocity, and for the wave we have a frequency, energy and momentum. But they can, he's saying that at one particular instant it can act as a particle, and at another it can act as a wave, but their property cannot be coexist at one point. So you cannot say that this point, at this particular point, it is behaving as a particle as well as wave. The particle and wave properties of radiation can never be observed simultaneously, and radiation sometimes behave as a wave, and when it is behaving as a wave, so wave has a property of interference, it has a property of a diffraction, and at the same time as a particle, then it will have effects as a photoelectric effect, Compton effect, and it has a wave particle dualism. So this is very important point. and this will be our last topic for today. And then okay, de Broglie hypothesis of matter wave. So we have learned that there is a ambiguity of a particle and wave theory. So how de Broglie hypothesized a matter wave? So the wave association with a moving particle is called a matter wave. He said if something is moving, if particle is moving, then we can say it is a particle wave or de Broglie wave. According to de Broglie, which is the concept came in picture in 1924, a moving particle always has a wave associated with it. So he says because particle has a property of mass, is a property of velocity, it has a property of kinetic energy. So he says that if a particle is moving, then a wave associated with it and motion of particle is guided by that wave. So he says that if a particle is moving, then there must be a wave associated with it, and motion of the particle is guided by that wave in similar manner as photon is controlled by wave. Now if a particle of mass m has a momentum p and lambda, the wavelength of the wave associated with it, then according to de Broglie hypothesis, we can say lambda is nothing but equal to h upon p. And we know my p is momentum can be written as mass into volume. And we can put the value of p over here, and that will come out to be h upon mv. Expression for de Broglie. Expression for de Broglie. Okay. So, according to Planck's theory, we know E is equal to hν. Planck has given his theory with a Planck constant and frequency, and he said E can be written as hν. But Einstein has said that energy can be defined in terms of its mass and speed of light, and he said that E is nothing but equal to mc square. If we combine these two equations, we will write hν is equal to mc square, and we can take, what we can take? We know that C is equal to mu lambda. C is equal to mu lambda, and from here we can get the value of mu, and mu value is C by lambda. We know C is mu lambda, and from here what we will get the value of mu, and that will come out to be C by lambda. So here hν is equal to mc square, h C by lambda. In place of mu, we can write C by lambda, and C by lambda is equal to mc square. And what we will do is we'll take h by lambda over here, and one C and cut with this C, and we're left with h by lambda is equal to mc. And that we will reshuffle it, and lambda will go up and mc will come down, and we'll get the final value as lambda upon mc. And this is for what? This is for when a particle is moving with the speed of light. But what about a matter wave? A matter wave or a materialistic particle will move with velocity of v. So in place of c, we will replace it with v, and we can write lambda is nothing but h upon mc. So this is my final value. Sorry, I can write lambda is if c is replaced by v, then I can write it m into v, and this is my more generalized form. This is my more generalized form. So this is my lambda upon h upon p into m into v. So different expression we can write from here. E is equal to m. I'll give you one example of it, and then we'll close the session for today. So what we know? We know energy is nothing but half mv square. So do one thing, and that is multiply and divide by m, and we will get mu square v square to m. What is m square v square? we know P is nothing but equal to mv, so we can write it as P square upon 2m, and this is the value we see over here. So my EK, so my E kinetic energy will come out to be equal to P square upon 2m, and from here we'll get the value of P square, and that is come out to be 2m EK, and from here you can say P is under root of 2m EK, and this is my final answer. So this is for today. Thank you so much for joining us. Thank you.